not the same place because that place is under renovation. So follow everybody to the road first of all. It's basically in that direction, a little bit to the right. Okay, so we quickly start with more discussions about disk accretion by Clement Bonneau. Did I say that right?
Yeah, almost.
Thank you.
Okay, do you hear me? Does it work?
No, it does
No.
not. It works, but you have to speak at least a little bit so you can get something.
I'll try.
Okay. Maybe here. Try now.
Okay.
Does it work? Stop.
Okay. So today I'd like to. Does it work?
Continue.
Okay. Yeah. First of all, I'd like to thank the organizers of the workshop for giving me the opportunity to present my work here in Jerusalem. So for those that I haven't met yet, I'm Clément Bonneau. I'm a PhD student at Leiden Observatory, working with Elena Rossi and Giuseppe Lodato. Unfortunately, they couldn't come to this workshop. And today, in this talk, I'd like to give our contribution to the open question of disk formation that has already been discussed in the two first talks. And then in the last slide, I will just give an advertisement about the work that is done on a different subject and will be on the archive tomorrow. So just to come back to the basic description of a tidal disruption, it happens when a star, after a succession of encounters with surrounding stars, is scattered onto an orbit that is parabolic, so with eccentricity 1, and that enters the tidal radius of the black hole, meaning that the penetration factor, defined as the ratio of the tidal radius to per-center distance, is larger than 1. And as we heard yesterday from Rem, what happens during the disruption is that the debris will get a spread of orbits, with half of them getting bound to the black hole, while the other half is unbound and escapes on hyperbolic orbits. And then the question of disk formation is the following. How do you get from this very eccentric and energetic stream of gas and remove enough orbital energy from it so that it forms an accretion disk on circular orbits close to the black hole? And this question is important because it's from this accretion disk that comes important electromagnetic signatures of tidal disruptions, such as the thermal flare that is due to accretion within the disk, and possibly relativistic jets that are launched in the inner regions of this disk. So the question that I like to answer is first, what the mechanism for disk formation? And it has been mentioned previously in the two first talks that a way of doing that is through apsidal precession that leads the first debris to fall back towards the black hole to precess and to collide with the part that is still infalling. And this leads to formation of shocks that remove orbital energy. Then another question I'd like to answer is on what timescale does the disk form if it forms? And also what's the structure of this disk? And this is also important because we've heard yesterday that the extension of the disk can lead to different blackbody temperatures detected from this disk. And finally, I will just touch this final point of the accretion within the disk, and more specifically by which, what is the rate of accretion within this disk, and is it set by the fallback rate of the debris or by some other rate? Okay, so ideally, the initial condition of such a simulation would be this one. However, as has been mentioned in the first talk, this is very computationally expensive. For the two standard parameters, so an orbit of the star of 1 and a mass ratio between black hole and star of 1 million. And an intuitive way to understand why it's computationally expensive is to say that the stream that is produced for these two parameters is very extended, so that is very expensive to resolve the different part of this stream. And so there are two possible ways of going around this problem, either by decreasing the eccentricity of the star artificially, which makes all the debris more bound, and therefore the stream is shorter and less easily resolvable, more easily resolvable. And this has been used in the previous talk, while another way to go around this problem is instead to decrease the mass ratio between black hole and star. And this has been used in the first talk by Rosanne. And here, this also solves the computational problem, because although the center of mass of the stream is still on a parabolic orbit, the time for the first debris to fall back towards the black hole is shortened, so that the stream has less time to extend. Okay, so the simulation that we did is using an SPH code called Phantom, doing both the disruption of the star on a bound orbit around the non-rotating black hole, and then follow the fallback of the debris where this formation takes place. And now there are three characteristics of this simulation that I want to highlight. The first is that we're using a relativistic potential that reproduces exactly the rate of apsidal precession. And so in this sense, our simulation is as accurate as a full GR simulation. But they're also cheaper, which allows us to probe a larger parameter space. And the second aspect that I want to highlight is that we are starting from highly eccentric stars up to an eccentricity of 0.95, which is close to the standard case of a parabolic orbit and will allow us to get insight into this standard case. And finally, as in the previous talk, we're using two extreme cooling efficiencies, either very efficient cooling encoded in an either thermal equation of state or a very inefficient cooling encoded in an adiabatic equation of state. Okay, so first I will show the results of those simulations with movies. Starting from a fixed stellar orbit of an eccentricity of 0.8 and penetration factor of 5, which means that the percent distance is 5 times smaller than the tidal radius. And in this case, the apsidal precession angle is very high, is of order 90 degrees. And this you will see in the movies. So first I will begin by using an efficient cooling. In this case, this is the gas and this is the black hole. As you can see, the gas precesses around the black hole, and at this point, this leads the stream to collide with itself, which transfers kinetic energy into thermal energy. But the assumption that is made here is that this thermal energy is radiated away very fast, that the net effect of these shocks is just to decrease the orbital energy of the gas. And this, after a circularization timescale of about 5 times the period of the star, leads to the formation of this thin ring that is located around the circularization radius, shown as the dashed circle. Okay, so in this case, thin ring forms at the circularization radius with a circularization timescale about 5 times the dynamical timescale of the debris. And here we find that there is only negligible ballistic accretion onto the black hole. And another thing that can be derived is what the thermal energy that is released during this disk formation. And in this case, it's just given by the difference in orbital between the initial orbital energy of the stream and the final orbital energy, which is the circularization energy. In this case, it gives about 10 to the 52 erg. Okay, now just to check whether apsidal precession is actually what drives circularization, I did the same simulation, but instead using a Keplerian potential. And in this case, as expected, there's no apsidal precession, therefore no intersection of the stream with itself, no shocks, and no energy loss from the gas. And so at the end of this simulation, there's the formation of this eccentric strip of gas that is way well outside the circularization radius. Okay, and finally, what I want to show is still using. Oops.
What is the parameter of gravitational unit?
10.
What was the parameter
10.
of gravitational unit?
10.
Okay.
And now, if I change the cooling efficiency to large cooling efficiency to inefficient cooling. Initially, what happens is similar to the previous case, but when the shock occurs due to self-intersection of the stream, the thermal energy, instead of being radiated away as before, is kept inside the gas, which leads to the formation of this thick and extended torus instead of a thin ring in the case of an efficient cooling. And this torus form on about the same circularization timescale as before, and it's located between the circularization radius, which you will see here, and it's within the semi-major axis of the star. Okay, so in this case, what we can learn from that is that the efficiency of the cooling determines what's the structure of the disk, and this disk is thicker and more extended for an efficient cooling. And what is also interesting is that in this case, we find that there is about 20% of ballistic accretion onto the black hole. And now if we do the same game as here, computing what's the thermal energy in the torus at the end of our simulation, we find that it's only 10% this, let's say, maximal thermal energy, which would give 10 to the 51 erg.
Just one quick question. Does your pseudo-Newtonian potential have the right ISCO for measuring ballistic accretion?
We are fixing the ISCO at the
Oh, you're just putting it in.
6 RJ.
Is any form of viscosity included in this code, or?
So there's artificial viscosity, which is used to resolve the shock. But then there's a switch that switch off artificial viscosity when there are no shocks. So when the disk forms, this switch is active, so there's no viscosity.
Shear viscosity, shear viscosity that is added.
No.
So this is SPH, right?
Yes.
So SPH is intrinsic viscosity which is very low.
Okay, you mean artificial viscosity?
You can call it artificial, it's numerical. It's big in the skin, there's a lot of this SPH skin induces a lot of viscosity.
Okay.
Another way to put that is, what's your smoothing length?
Here we're using 500,000 particles, but the smoothing length, well, it depends on the density of the gas. So it's difficult to say. Here it's using 500,000 particles.
Using an SPH, there's always an averaging.
Mm-hmm.
And the question is how
And the
wide-
number of neighbors, you mean? It's
When you calculate both pressure and density, you're averaging over some number of particles, which is
I think it's 58 particles. Okay, just to continue, I'd like to continue on giving more information on the structure of this torus. So as I already said, it forms between the semi-major axis of the star, which is 1 here, and the circularization radius, which is 2/5 here. And another important thing is that there is centrifugal support in this torus only in the inner regions. And also the pressure support in all the torus is only of order 10%. And combined with the fact that we find that 91% of the gas stays bound, which is the majority of the gas, it means that this torus is not in equilibrium, and that this outer region is likely to, at later time, fall back towards the inner region, which could lead to shocks and possibly more emission. Okay, so now, so far I just considered one orbit for the star. I'd like to change this orbit, keeping the assumption of efficient cooling. And I'd like to change this orbit in 2 ways. First, by increasing its eccentricity, keeping the penetration factor fixed, and then by increasing instead this penetration factor, or decreasing the penetration factor, meaning increasing the pericenter distance. So what happens in the first case? Just like to pause here to say that this is likely to be similar to the case of a parabolic orbit for the star, because this is the highest eccentricity that we considered. And also the pericenter distance is unchanged, which means that the apsidal precession is still high, about the 90 degrees. And the combination of these two facts implies that the stream collides very early. It doesn't have to chase itself, like in the previous case, to collide. And this leads to disk formation that is faster than in the previous case of order of the dynamical time of the debris, so of about 1 times the period of the star. And now if I do the other game of increasing the penetration, the pericenter distance. Here instead the apsidal precession angle is changed and it decreased from about 90 degrees to 10 degrees. And this leads to shocks that happens further from the black hole, where relative velocities between the two components of the shocks is lower, and so therefore these shocks are weaker and less efficient at removing orbital energy from the gas. So again, a disk forms, which is a thin ring around the circularization radius, but this disk formation is slower than in the previous case. Okay, so that's the
The centimeter axis for both, what is the difference, the ratio between the two?
this is this is 500 solar radii and 400 solar radii.
The left is closer.
Well, in terms of semi-major axis, yes, but in terms of percenter, this one is closer. Okay, so that another conclusion of our work, which is in the case of bound orbit. In the case of bound orbits, the circularization timescale is determined by the stellar orbit, being shorter in the case of larger eccentricity and longer in the case of larger percenter. And now I would like to maybe get more speculative on in trying to understand to what extent these results can be extrapolated to the case of parabolic field. And what I will say, if I come back there, is that the main difference between this case of a bound orbit and the case of a parabolic orbit is that in the case of parabolic orbit, instead of having all the debris involved in the disk formation, there is a long stream of gas here and only its tip is involved in the disk formation. However, if we keep the penetration factor or percenter distance fixed, this apsidal precession will stay large, leading to shocks close to percenter, which will drive the disk formation in a dynamical timescale. And so one way to extrapolate these results in this case for large penetration factor is to say that due to shocks that happen still at percenter, the circularization timescale is about the dynamical timescale of the most bound debris, because those are the ones involved in circularization in this case. However, for the case of beta equal 1, this is much less clear because, as I showed you here, due to the slow apsidal precession, the shock happens at apocenter of this debris, so they are weaker. But it's even worse in the case of a parabolic orbit because the apocenter of the most bound debris is even further than in the case of the bound orbit that we considered, by a factor of about 2. So in this case, the circularization timescale is likely to be much longer than this. So maybe a few tenths of T-min. Or another possibility is that instead of forming a disk at the circularization radius, it forms an elliptic disk, and that will be discussed in the talk, in the next talk. How much do I have left?
More or less done.
Okay, I'll switch this. So yeah, I'd like to finish by advertising a work that we've done recently in investigating what's the interaction between the bound part of the stream with the gas surrounding quiescent black holes. And what we found is that Kelvin-Helmholtz instability, which is a sharing instability between the stream and the ambient gas, can in some case lead to the dissolution of this stream into the ambient medium. And this effect is enhanced if the density contrast between these two components is decreased, which occurs both for massive black holes and for giant stars. And so previously it has been argued that above 10 to the 8 solar masses, where mean sequence stars are destroyed within the Schwarzschild radius of the black hole, leading to no substantial emission. Above this black hole mass, the black hole diode would change from main sequence stars to giant stars. But instead here we argued that as these two conditions are satisfied in this region, all these events involving both giant stars and massive black holes would be much more difficult to detect than expected due to this Kelvin-Helmholtz instability. So I would be happy to discuss this later. Thank you for your attention. The main physical difference. Oh, there's. Yeah. So in this case, we found that there is a slight dependence on the resolution of the simulation. You use the 100,000 particles, and we use 500,000 particles, and we found that this quantitatively is similar. Yeah, there's this formation occurs maybe in it requires one more evolution to circularize when the resolution is increased. And we find that this is actually converged result. Yes.
So there's a paper by Kaufman and Nixon in the Festival months that proposed that there's clumping in the stream that leaves areas due to a gravitational instability. Do you see any evidence of clumping in your simulation?
We are not considering, we are just using a simple analytical model which treats only Kelvin-Helmholtz instability.
Oh no, I mean your SPH calculation. Do you see
Oh.
any evidence of clumping in the SPH calculation?
No. That's the short answer.
Self-gravity and I think the clumping.
Yeah, so self-gravity is in. So something that I didn't say is that we include self-gravity only when we study the disruption of the star. And when the first debris falls back towards the black hole, we're just switching off self-gravity.
Oh, you switched it off entirely.
But
Yes.
if you wait until the first return, that's study long enough to need to be clumping the $100, right? Because that's right after the disruption process.
But I don't know when you're turning off self-gravity. When are you turning it off exactly?
It's because it's computationally faster.
When?
When? So basically, in the simulation that I showed, self-gravity is turned off.
At what time?
What time?
When the first debris reaches the black hole.
When that reaches area, that's when you switch off gravity.
Yes,
Self-gravity
yes.
at that point. Okay. So
But
there
it-
should be clumping principle.
But in our case, I think the main difference between the work of Nixon is that we're using bound orbits, and the material take much less time to come back to Paris center, and so self-gravity, I think the clumping in this case is less likely to happen.
But on the other hand, the linear mass spectrum is high, right? With the decrease in sensitivity.
Their latest paper suggests that some transitions right around gamma of 5/3 before you go to clumping to not clumping. But you guys don't see it that like you guys don't know about it.
Okay, last question. Yoni.
Did you share the thread on here
That's a good question, and we didn't check that. But I think what you mentioned is that the main effect of magnetic field, if I understood correctly, is to change the transverse, the balance of forces in the transverse direction. And does it also change the dynamics in the longitudinal direction?
You have field lines that are oriented parallel, like with the stream itself. And I think the question of the KD as the typical configuration of the field, right? The tangent sigma where the field lines are parallel to the intersection of the KD. But you do have background magnetic fields too, right? That also plays a role in the KD stability.
Okay.
Okay, thank you very much. So we have one more talk, and after this talk, we're going to the physics colloquium. After the physics colloquium, we're coming back here. So the last speaker before we leave is Tzvi Piran. I guess some of you may know Tzvi. This is more or less to the date, the 20-year anniversary of my first published paper ever, which is of course with Tzvi. But it's all long and forgotten, and today is known as the father of microprocessors. She's going to be after the colloquium, it wasn't clear we're coming back here, and there will be sandwiches with a light lunch in the lobby.
Yeah, the viscosity was also, I mean, it's almost solid.
I have to comment after the third. That's not true. That's not what we do.
Historically, this is what's happening. Now this is not the case, but historically, I would say, I think this was the case. And the question, and then you find these guys. So this is one of the best examples. So you see the expected people in the structure. But then there is a but. And I'll talk about the but. And to understand the but, I return to some pictures, to some results that Korean shown us yesterday, but for those of you already seen here, just to remind, the tidal disruption that takes place, the tidal habit, is about 10 to 30 RT for typical parameter of 10 to the 6 solar masses and 1 parameter second. And this is around 10 to the first centimeter, the typical parameter. And the most bound return metal goes up to about 6 centimeters value, which is larger by the ratio of the mass to the ratio of the mass to the down by 2/3 compared to this value. So this goes to about 1,000 RT, which is 10 to the 50 centimeters, which is large factor. And this is 52 values per month. Now again, the standard model assumes that very quickly inform the returning matter. Oh, I don't have my what is the
Sorry, I kept it.
Well, I can tell you now that once I did the same thing, and I was going out of the room after my talk, and then somebody came and told me, oh, but you didn't cite my work, and I did this, and I did that, and I said, no, but your work is not relevant, and the microphone was still on. Nobody heard the speaker, everybody heard this conversation. This was fairly embarrassing. So this did not happen here anyway. So, okay, so what are the theoretical expectations? The theoretical expectation is that we have a shock near the tidal radius, that and this shock circularizes very quickly. And the implication of this is that if we have an accretion of about solar mass, then with reasonable efficiencies from this accretion disk, we should see something like 10 to the 53 ergs coming out. And if the disk is around RT, which is 10 to 30 gravitational radii, then the typical temperature should be in keV, so it should be in X-ray. And the velocities should be around 50,000 kilometers per second or larger. The typical velocities involved with such a small accretion disk. So this is the expectation. Now, what do we see in this object? And actually, most of my all the talk will be focused on the optical UV transients, and there are also X-ray transients, but I'll be talking only about the optical UV transients. So what do we see here? We see a peak luminosity of 10 to the 44 ergs per second, a temperature of about 50,000 degrees, and the line width of few thousand kilometers per second, about 5,000. And the total energy release is 10 to the 51 ergs. And if you combine these three factors together, then the expected emission radius, just some simple black body arguments, is around 10 to the 15 centimeters, which is about 1,000 RG for this system. So this is definitely not exactly what we see here. And the question, what is happening here? So I want to remind you some old simulations which actually influenced me. This is simulation by Stefan Rosvog, and you see very nicely what is happening. This was actually a neutron, white dwarf around the black hole with few 100 solar masses, and you see the returning stream, and you see the returning stream, and you don't see an accretion disk. Now, it is true there is no precession here, but even so, this is SPH with a lot of intrinsic viscosity. The mass keep going back to large radii, more or less of the same order of the initial R0, the initial radius to which the mass was, most bound material was going back, and this does not happen here. So it is clear that at least in this simulation, there is no process that dissipates energy here and produces a shock and produces the disk. And now it is realized, but early on it was not so clear, and there are papers making wrong statement that you have to dissipate angular momentum in order to produce a disk. What you have to do is you have to dissipate a lot of energy to produce the disk. The angular momentum is right there. So that's why the subtitle of this talk is Desperately Seeking Energy Dissipation at RT. So this is what we need. But let's see how much energy I will get from this energy dissipation, and this was already mentioned in one of the talks here, that if you want to form a disk around RT, which is 10 to the 20 gravitational radii, then you need to dissipate Gm over RT. The initial energy of the matter is Gm over R0, which is practically zero in this compared to that. This is 1,000, this is 20, so this is practically negligible. You have to dissipate all this energy, and this is about 10 to the 52 ergs. This is already too much. So because we don't see this much energy, so we need a strong shock here and the strong shock should dissipate a lot of energy. Now, these are the simulations that Rosen and Hotaka did, and this is the also the logo that we took the logo from this simulation. And so this is the movie of this returning mass here, now with more sophisticated hydrodynamics. And again, there is very little dissipation here at the center. The white regions are the regions where energy is dissipated. And you see here in the simulation that energy is dissipated in large distances from the center, and a very little amount of energy is dissipated near the center. So at least in these simulations, we didn't find the needed dissipation, and this is full GR, but indeed with these parameters, the shifts, the upside shifts are not so large. So this is still an open issue in my mind, what they will do. So what is the observational problem? And I already mentioned it here several times. This is what is expected if you form a disk. If you form a disk, this is what you expect. Temperatures of 5,000 degrees, you see 50,000. Radii of about 10 gravitational radii, you see about 500. Velocities larger than 50,000, you see 5,000. Energy, total energy of 10 to the 53, we see 10 to the 51. So I compare these two numbers, and I call this an inverse energy crisis. It is inverse because usually when you say an energy crisis, you need energy and you don't have enough energy. Here it's the opposite. There's too much energy in the system, and you see much less than what you expect to see. So this is the crisis, and I want to stress that even the circularization energy will cause by itself, if you circularize, this by itself will cause the same, slightly weaker inverse crisis, because then just the circularization should release 10 to the 52 ergs, which we don't see. It may be coming somewhere, it may be swallowed by the black hole, but we don't see it. So the solution for where do we see the radiation is outer shocks, and Gilad will talk about this later, and Rosen also mentioned this. It's actually, we suggest that the collision of the incoming stream with the returning material, this is, which happens at about a few hundred to 2,000 gravitational radii. This is the region, this energy dissipation has the right amount of energy at the right time scale and so on, but I will not talk about it. I call this model the what you see is what you get model. You see this, you get it. But let's skip this, and I am just stating that suppose the accretion disk doesn't form, and we see this outer shock, but then we still have this remaining energy. Where is all the energy? Where does all the energy go? Now, one way to hide the energy, and this is the Polish donut model. And by the way, if you show this in Israel, nobody will call it Polish donut. It's called sufganiya, and this is just the time of the year that we are supposed to eat it, and we'll eat it during the conference, don't worry. So this is the Polish donut, and this is the structure of the Polish donut. It's a thick disk, and Oleg here has worked a lot on modifying this model and working out the details of this model. So it's a thick disk. Energy is generated here, but it's all swallowed, advected into the black hole. It's swallowed by the black hole. The problem with this model, it requires a lot of angular momentum to support itself. To have such a structure, you need a lot of angular momentum. And in the system, we don't have a lot of angular momentum because the typical angular momentum is small. It's of order of the angular momentum at the tidal radius, which is small. So it's not clear that you can build such a structure. Now let me remind you something that you probably learned in graduate school. This is the general relativistic effective potential around the black hole. This is how it looks. So what we have here is contours of fixed angular momentum, and this is energy, and this is radius, and these are points of deflection. Each particle on this point was deflected, and this point here, the minimum of the potential, are the circular orbits. And the standard accretion disk theory, the Keplerian accretion disk theory, that Julian described yesterday in the school, but everybody here knows, is that the particle goes from one circular orbit to another, and when you go from one circular orbit to other, you lose both angular momentum and energy. And until you get to this point, which when I was young was called RMS, but somehow it has metamorphosis and it's called ISCO. I don't know why ISCO is nicer than RMS, but this is what happened. So this is the ISCO, and the matter falls from the ISCO to the black hole. And then there's also a question how fast it forms and what happens here. But basically, this is the end of the regular accretion disk, and the matter falls here. And the efficiency, which is usually estimated, is taken from this value. It's the energy of the ISCO, because you definitely dissipate this, and you may get a little bit of that, but that's a different story. So this is the standard accretion disk, but you can think now about another accretion mode. Suppose that you have a system which is a lot of energy compared to the angular momentum. So you have a lot of energy but little amount of angular momentum. So you will move an elliptical orbit. So this is an elliptical orbit. Now suppose that I take this particle and change a little bit the angular momentum. It will go to this trajectory, go over the top of the potential here and fall into the black hole here without losing much energy. So this is another way to plunge into a black hole without dissipating a lot of energy. So this is elliptical accretion, and this is why I call this the Jerusalem bagel. Not exactly to scale, but this is something like that. You can put it here, and okay, so this is the Jerusalem bagel. By the way, you have to eat it with this za'atar, and it is not clear to me what is the physical meaning of the za'atar. So this is an open question for the audience. What is the role of how to add this? Maybe this is the magnetic field. I don't know. So this is a more picturesque way to do this. And so we are talking about elliptical accretion. And what happens is the following, that the question whether you have circularization or elliptical accretion depend on the comparison of the rate of dissipation of energy versus angular momentum. If you're dissipating, most of the dissipation happens here, then here you dissipate little amount of energy and large amount of angular momentum. If most of the dissipation is here, you dissipate lot of energy and small amount of angular momentum. I know that you're standing, I'm just finishing in time. So this is circularization. If you lose a lot of energy, things become more circular. If you lose more angular momentum, things become more elliptical. And now is the question to balance, to compare elliptica, to compare, is this possible? Is it possible to the mathematical question or the physical question that we ask in this model is, can you dissipate along this bagel more angular momentum more rapidly than energy? If you can do this, then you go to this elliptical mode. If you cannot do this, you circularize. So this has to do with the rate of dissipation of energy, and this is the stresses here. And you can compare it with the rate of dissipation of angular momentum. It's almost the same formula, but here you have this factor of r times t, because which relates the direction of the force and the tangent to the motion. So this is the big difference between these two quantities, and this makes all the difference. Now you can play with these formulas. I don't have time to do all the games here. You replace this relationship by the one of the Alfvén velocity. This is the integral of the density divided by integral of the magnetic pressure. This is actually the one of the Alfvén speed squared. And you can do these things in both, for both rates of dissipation. And you can go further on with more, so this is estimates of the rate in this is happening. And this is basically the formula that we want. How long it takes to dissipate the angular momentum that we need, and how long it will take to dissipate the energy that we need. And I'll just show this last formula. You can compare these two relationships. They are almost the same, apart from this factor here, which is of order 10. So this rate of dissipation of angular momentum is faster by about, this is the number of orbits that you need. So you'll dissipate the angular momentum in about 10 orbits, while you dissipate the energy in about 100 orbits. This is a very rough estimate, plugging typical numbers here. Most of the numbers do not really matter because you have the same values here and there, but this is the biggest difference. And so we conclude that it is possible, just from this order of magnitude, that this is happening. And so we suggest that this is an alternative. From culinary point of view, this is definitely much healthier than this in terms of calories and so on. This is also a lot of oil. But here, this is low angular momentum, and heat is effectively not generated. This is high angular momentum, and heat is swallowed, both by the customer who eats it and by the black hole. And the conclusion is that the TDE's observations are inconsistent, at least with the simple version of the standard model. You may have to sophisticated versions, maybe, but the simplest version, you have to modify it. This model states that circularization is slow, and it is the energy crisis is naturally solved by elliptical accretion, in which you simply plunge into the black hole with a lot of energy, without dissipation, without converting this energy ever to thermal energy. And of course, there will be some energy, there will be some dissipation, and some of it we'll see in another channel. But this is not the main thing that we see. Thank you. And we have to...
We have time for one quick question.
Why do I get that? Okay, thanks. So, okay, so it makes sense that, of course, if you basically have an instantaneous impact of apoapsis, your orbit returns to the point of impact, you will always return to the apoapsis. That just means you shrink the periapsis. But and you can have basically, eventually have a sufficiently eccentric orbit that you plunge directly and have accretion. The question is, though, in the process of doing that, you are changing the orbit elsewhere. Don't you create stronger and stronger shocks around periapsis as well? So even if eventually all the impact of the apoapsis, before you actually start accreting, don't you have trouble near periapsis?
Yes. Yes, but. So let me reiterate the question. When this is going on, as you become more and more elliptical, suppose that this is happening, as you become more and more elliptical, more and more action is happening here because the motion is getting closer to the black hole, so you feel stronger GR effect. It will be only at around, you have to get to less than about 10 RG before things get interesting. So if you're beginning at 20, for example, until you get to less than 10, it's not so critical. Once you get to less than 10, then things start to be interesting. And then you get strong deflections, and then this ellipse will be turned, the returning matter will turn, it will interact here or somewhere around here and may cause something. However, it is not clear what is happening there. And this is, so we think that, in my mind, the question is completely open for detailed numerical calculation, because it is true that you dissipate energy, but you also dissipate angular momentum at this moment. So it is possible that after this interaction, you dissipate energy and angular momentum, and the matter go directly into the black hole. It's not necessarily like this, it is possible. Another thing which is possible, that you generate heats there, but the system is very small, very optically thick, and then you form a small donut inside this bagel, and the donut is does not let energy go out because it's optically thick and so on. So it is true that what happens at the last phases, it's not clear. But the early phases, here, this is mostly supported by this. This is mostly composed of highly elliptical orbit, this thing here. And the first phase, I think the elliptical idea is working. And I think we just opened the discussion for a new mode of accretion, and now we have to work the details. It may turn out that at the end something else happens.
Okay, we'll have to keep the discussion session. Thank you very much. Follow everybody else. You go out of this building, turn right, all the way to the end, or before the end, and then down the stairs, and the building is on your right.
So you're basically making it tougher for the part that is being forked up to eventually make it down. So it's basically,
But you get up and stuff.
it's basically sacrificing like maybe half of the material.
Well, I mean, in standard accretion disks, you accrete most of the mass because a very small fraction of the mass is able to absorb all the angular momentum.
No, but that's still not efficient because there is an unspecified reservoir kind of magic.
כן.
10 ב-51.
כן. מה?
אולי זה 10 ג'ופיטר מס, זה לא סולר מס. זה לא עונה על הטמפרטורה והמהירויות.
זה יעשה לך את כל הדברים האחרים גם כן, ישגע לך את הדברים האחרים, זה ישגע לך את הטיימסקייל,